represented by shaped laser pulses, and we do the shaping in the frequency domain. So the combination of manipulating qubits with quantum logic gates allows us to perform quantum algorithms. And I'm not going to go into the details of the quantum algorithms. I'm more interested in this aspect here. So if we apply some laser pulses that are shaped to represent these quantum logic gates, as I've shown here, so the ACNOT 2 is a specific gate. Applied in some order, we can apply some algorithm, and then we look at the system in the end to see what the resultant qubit transformations that took place. I look at 2 qubit operations here, so we have this vector notation here, Q1, Q2, the 2 qubits, and we have this respective 4 qubit representation by manipulating Q1 and Q2. Each one of these qubits can be represented by a set of rovibrational states, represented here by nu and j. And so on the diagram to the right, we have increasing nu, vibrational number, and increasing rotational number on the bottom. And in red are the qubits that I chose to represent by the rovibrational states. So for instance, the qubit 1,1 is represented by the rovibrational state 1,0. An alternative representation by Tsubushi and Lemos is shown in gray. And the disadvantage of this kind of representation is that if I want an excitation between qubit 1,0 and 1,1, I need to absorb 2 photons through here, right? Our cyclic kind of representation here requires only 1 photon transitions in order to excite between qubits. And keep in mind, we're shaping in the mid-IR, so we are obeying these rules here. And that just means that there's excitations, in this, at least in this diagram, excitations along the diagonal only. So to show how a quantum logic gate works, I just want to kind of focus in on the main feature here, and that is a single laser pulse must be optimized in order to carry out all the operations within the quantum logic gate. So for instance, if this quantum logic gate requires a qubit transformation from 0,0 to 0,1, or vice versa, or alternatively, a qubit transformation from 1,0 to 1,1, and vice versa, this must be all carried out by the same laser pulse. And it turns out that this kind of operation is actually the NOT 2 quantum logic gate. And I've just kind of shown it here in shorthand. On the right in this kind of table here are a set of other quantum logic gates. Relevant to my talk, I'm going to talk about the NOT 2 gate and the ACNOT 1 gate. And they're similar in the sense that they both have the same qubit transformation from 0,0 to 0,1. But in the case of the ACNOT 1 gate, the transformation of the qubit 1,1 or 1,0 essentially remains the same. So there's no state alteration there in the case for the ACNOT 1 gate. How does this relate to a diatomic and population change? So I just wanted to show that here. So in this graph is state population versus interaction time with the laser pulse. And in black and red is the qubit 0,0 and 0,1. And they're somewhat superimposed, but inevitably, if one starts in the qubit 0,0 with a population of 100%, the other state is 0, and essentially they get switched. And at the end of the pulse interaction, you're either in 0,0 or 0,1. Alternatively, the qubit transformations 1,1 and 1,0 also remain the same after the qubit transformation, but there are some subtle population transfers in between. Of course, if we have a more complicated laser pulse, we can have a more complicated pathway, just to illustrate that it's not as simple as the one I've shown before. So I keep on talking about laser pulses, so here's a I don't want to go into too much mathematics, but here's a mathematical form of it. We are shaping in the frequency domain, and we have discretizations in frequency, so this smooth Gaussian distribution is actually discretized. And basically this form of the equation represents amplitude variation from 0 and 1. The center exponential here is basically the Gaussian profile, the Gaussian pulse here. And the last part here is just the phase variation, and that varies between 0 and 2 pi. So in the diagram I've just shown the full width of half max, delta mu, but more importantly are the fact that we can choose the frequency width and the number of frequency components incorporated in that laser pulse. What this means is the following. We're able to choose a specific frequency width. On top of that, we can choose a certain number of frequency components. And each frequency component that we choose has then a variation in amplitude and phase. So there are a lot of different combinations and possibilities. Just to illustrate this, here's an example laser pulse. It looks quite simple. It just contains some frequency here and some side wave frequencies. In the time domain, it looks like this. Okay? I can generate a more complicated laser pulse here. We have a number of frequency components being optimized, and pulse and the time domain is, again, more complicated. Take-home message here, we just have so many dials. How do we determine the optimal laser pulse to represent the quantum logic gate that we're interested in? So one could do this through brute force, just calculate all possibilities. Of course, that is not always feasible. For instance, if I have 51 frequency components and 2 amplitude and 2 phase components, for instance, say the amplitude varies 0 or 1, and the phase is 0 or pi, I would have 4 to the power 51 total combinations. So it's kind of unreasonable to calculate all of them. And generally, use an optimization algorithm. What that allows us to do is determine the optimal pulse shape without having to sample all possible combinations. In our case, we use the genetic algorithm, the GA. It's also used experimentally. The GA works on natural selection, so specific traits become more common from one generation to the next. What this means is specific amplitude and phase components of laser pulses become more and more relevant from one generation to the next. So we're kind of weeding out the relevant amplitude and phase structure from one generation to the next. So I'm going to show this in an illustration. On the left here we have a bunch of 16 circles with varying size. So you can think of these as laser pulses. And the size determines how well the laser pulse does at representing the quantum logic gate that we're interested in. So the first step in the GA is tournament selection. So the individuals that do a better job at representing the quantum logic gate that we're interested in breed more often. And in this diagram, this is represented by the size. So this large individual here would breed more often. You can think of it that way. And as I alluded to, there is breeding. So based on tournament selection, 2 individuals will come together and their amplitude and phase information will exchange to produce a new individual. And this new individual is then put into the next generation. So we're trying to populate the new generation of individuals from their quote-unquote laser parents. And we do this 15 times. There's 16 individuals here, so we need another individual to constitute our new generation. And that is our elite. And basically, we're just taking the best individual in the current generation and just automatically throwing them into the next one. So in this case, this high fidelity or high performance laser pulse here would automatically get put into the next generation. So as this diagram shows, the laser pulses get thrown into what I've labeled the quantum dynamics. And here we determine how well the laser pulse does at representing the quantum logic gate that we're interested in. And this is represented by a fidelity. It's just a number. And this number helps the GA to determine how well that laser pulse does so that it can do the tournament selection and all these kind of other different setups in order to optimize. This cycle continues for, say, n generations. And at the nth generation, the program stops, you look at the output, and you pick the laser pulse that does the best, and that's your optimal laser pulse. What is this fidelity value? Because this is quite important, actually. So here's the equation for the fidelity. As I said, fidelity is a number, in this case from 0 to 1, it's normalized, that represents how well the laser pulse does at representing the quantum logic gate that we're interested in. It's summed over 4 because we have 4 qubit representations. And the first part here represents the interaction of a qubit with the laser pulse at time t, so at the end time.